Good morning and welcome to the Nexperia Power Live event. We're live here on the industrial channel for the next 2 hours, ready to discuss all things power MOSFETs. And we're starting with design insights for battery powered motor control and key MOSFET parameters. This particular discussion is scheduled for 25 minutes. We'll begin with an introduction and then open the floor for questions. So please do join in. All contributions are anonymous, so you can ask any questions to our experts about the designs and projects you're working on at the moment, but also do feel free to share your own knowledge and experiences. Questions can be asked throughout the session using the orange speech bubble in the bottom right-hand corner of your screen. We'll start with our first presenters of the day. We've got Stephen Waterhouse, Product Manager, and Samit Ahmed, Senior Applications Manager, both from our Power MOSFETs division. And with that, I'll hand over to Stephen to begin.
Okay, thanks for joining the online session this morning. I'm going to present roughly about 10 minutes of what we think are important parameters in motor control applications. It's a short presentation, and then at the end, as Kelly said, we have a 10-minute session where we'll answer any question and discuss applications in detail. So for this session, we're going to focus on the motor control market and products in the range up to 100 volts and up to about 10 kilowatts in power. This market, it's quite wide. We see some products which are cordless power drills, which are quite low power, all the way up to material moving equipment, forklift trucks or golf buggies. And in between, we have industrial cleaning, e-bikes, wheelchairs, some home appliances, and some gardening tools. So it is quite a wide-ranging mix of products we see in this market. And each of these usually has a lithium-ion battery, not always though, which will run a BLDC motor. I'm going to now pass over to my colleague Samit, who's going to talk a little bit more in detail in what we believe the parameters are that are important in these applications.
Good morning, everyone. Thank you for joining. Thank you, Stephen. My name is Sami. As Stephen mentioned, we have selected what we believe to be the key parameters for motor control specific applications. And we're quite happy to discuss any other parameters that you think are relevant or appropriate for the motor control drive. The first item selected here is a VDS. Perhaps not the fanciest of parameters, but nonetheless, it is the first parameter that one picks for the MOSFET as it needs to fit the power supply or the supply of the system. Normally, it is selected to fit the supply, which is about 80% of the rating of the MOSFET. But then again, that's what we see as a trend. If you have another approach, please share with us. The VDS that we provide in our MOSFETs come in a various range. The 30 and 40 volt seem to be the most common ones. And we have other range, such as a 55 volt device suitable for a 36 volt battery. 100 volt devices for the forklift, truck, and light electrical vehicles, as well as other voltage range that we can discuss outside this 10 minutes presentation. Perhaps one of the most important parameter in the MOSFET is the ID current rated. We mention in here most relevant to management of fault condition and locked motor, because it is obvious that one selects an ID rating suitable for a nominal current. However, it is now accepted that stalled current or stalled motors, as well as fault conditions, are part and parcel of the normal operation of the application, and therefore the rating of the maximum rating of the MOSFET is very important. The thermal management, obviously, with these high current capabilities, that generates or induces the power and therefore heat, becoming one of the most important item for the MOSFET to handle. Now, various approaches are necessary to be present at the same time for the thermal management of the MOSFET. one of which is the low R theta, the thermal resistance of the MOSFET. The LF pack does provide one of the lowest thermal resistance to deal with the heat generated by these high current levels. Increasing the junction temperature. Normally, non-automotive MOSFETs are rated to 150 degrees. Nexperia MOSFETs have got the improved temperature rating to 175, giving that extra room for thermal management. Combine this with the low RDS on, again, helps with all this thermal management. Now, why is thermal management important? Because ultimately, temperature or thermal is what kills a MOSFET. Next slide, please, Stephen. Spike control. It is perhaps inevitable to have spikes on your application on a design. What we tend to do with our MOSFETs is to control the switching where the switching is nice and smooth, avoiding any spikes. We tackle this into two fronts, or two major fronts. One is the smooth recovery of the body diode characteristics of the MOSFET, reducing the QRR, where minimizing the power losses, as well as having a MOSFET dealing with repetitive avalanche in case the spikes are inevitable, are coming from the parasitics in a circuit. This brings me to the next parameter, which is the avalanche rating. Now, why is avalanche rating important? As I mentioned, the MOSFET itself can only control how the MOSFET behaves. We understand that the circuit has got parasitics and other parameters that do contribute to the spikings. And therefore, for those, a MOSFET that has a strong, robust avalanche rating, as well as repetitive avalanche, is quite important for those applications. Next slide, please, Steve. The gate drive, we provide both the logic level and the standard level. Now, logic, depending on the application, the preference comes in for logic level if it's driven by a 5-volt circuit, where it deals with the collapsed batteries, where low levels of the supply is necessary. However, standard level can be preferred to avoid false triggering. We would like to reassure you that both of them come with a maximum rating of plus or minus 20 volt, because that's one of the concerns if logic level is chosen. The safe operating area, the technology that are provided in our MOSFET provide one of the most strongest SOA in the devices. These are important in situations where sometimes are not thought of. If the MOSFET is switching off with trying to control the high current going into the circuit, it is put into linear mode, and therefore the SOA is most important for that application. The size of the MOSFETs come in various. We have the LF pack 3x3, LF pack 5x6, and 8x8 because of the existing motor sizes out there, and therefore for different applications we have the right size that fits the purpose. And with that, I'll hand back to Stephen. Thank you.
Thanks, Sammy. So I'm going to quickly go through some of the innovations that Nexperia have developed for battery-powered motor control. One that we're quite keen to promote is the high current capability. And we've got a session immediately after this session in half an hour or so, where we talk about the high current capability of the LF pack. And this goes up to 380 amps. And we can see there we've got a 0.58 milliohm device, 30 volt device, which has that rating. We can demonstrate that rating and have some online videos, which you can see as well. We've also developed a package which was specifically to address the UL 2595 specification. So this is specific to motor drive applications where you need increased creepage and clearance distance. And again, we've got two parts which, after this creepage and clearance, but again, the package is now released and qualified if we have other products which require it. At 100 volts, we've developed the low QRR platform, and you can see there QRR gives you additional energy loss. So if you reduce your QRR, you get lower energy loss, but it also helps with your reverse recovery spiking, which will have an impact on the EMC performance as well. For high power applications, we've developed an LF Pack 88. This is a toll or D2 pack replacement, and this is rated up to 425 amps. So for these very high power applications like the forklift trucks, this is an ideal package. We've also got the LF Pack 56H, so this is a half bridge package. So this is two MOSFETs of similar sort of size, so say 4 milliohm, and they're in a half bridge configuration with the internal connection, reducing the inductance and the interconnection resistance. And another development we're really excited about is our match VT or current sharing devices. So we constantly ask for match VT for MOSFETs used in parallel. However, we've developed a platform which a technology which actually removes the need for matching VT, but gives you this excellent current sharing capability. And again, we've got an online session later today, which will go into more detail on this technology. So just to highlight some MOSFETs, which we see as suitable for motor control. So on the left there, you can see we've got a nominal battery voltage. So for up to 14 volts, we'll typically see a MOSFET VDS rating of maybe 25 volts. For 18 volts, we see a 30 to 40 volt rating. And you can see there at the 40 volt rating, we've got an LF Pack 88 device. This is 425 amp rated. It's a 0.55 milliohm in an 8x8 package. For the LF Pack 56, we've got we've got a 30 volt device, which is 0.58 milliohm. And again, that's 380 amp rated. And even if we had space constrained applications where you'd use a 3x3 package, we've got the LF Pack 33. So it's a 1.6 milliohm device, and that's 160 amp rated. I'm not going to go through all of these products, but this is just an overview of the type of products which we developed for these very harsh applications that motor control requires. That's the end of my presentation. Hopefully we've got some questions, so please let us know if you get any questions. It doesn't matter whether it's application or regarding the MOSFET itself. Thank you.
Thank you, Steve and Sammy. So just to remind everybody, you can ask questions by using the orange speech bubble in the bottom right hand of your screen. We've already had a couple of questions in, so let's start. Stephen, how do the Nexperia MOSFETs behave in fault conditions?
Okay, so under fault conditions, there's several fault conditions we consider in these type of applications. If you remember at the start, I mentioned that these are for battery powered motor control applications. So usually with lithium ion, it's a very unstable application. Needs very tight control. So you use a MOSFET to isolate the battery pack. You may also have some secondary fusing, whether that's a chemical fuse within the battery pack or an electrical fuse to isolate as a last resort. But what you need to be able to do is you need to be able to switch that fault current off as quickly as possible. And in doing that, and this is in excess of 300 amps, usually the fault current, the MOSFET would normally go into linear mode due to circuit inductances or sometimes avalanche. So the MOSFET needs to be as robust as possible in linear mode and avalanche conditions. And because our MOSFET has superjunction technology, our low voltage platform is superjunction technology, we have inherently good SOA performance. For some applications, we have extended SOA capability, and this gives you up to 4 to 6 times the capability. So that's on the battery protection side, where we see most of these sort of fault conditions. But if you look at the motor drive itself, Then there's situations at startup. So if for example, it was a high power drill, you may have a locked rotor, or during startup under very extreme conditions, you have a very high current demand going to the motor drive. And because the motor's locked or stalled, it would be seen as a dead short. So you have a very high current demand at that startup. And for that, you'd want a high ID pulse rating for the MOSFET. So you'd want to pulse that motor drive to get things started, to get the motor started. So a very high ID rating is required. And then again, if you have any noise in the circuit, depending on the wiring, it's not always possible to put the motor drive as close as you would like to the motor. And sometimes you see some avalanche just due to circuit inductances. And again, most of that will be back on the battery protection FET. But yeah, these are the typical fault conditions we would see. What that means for the MOSFET is it could burn out, because all of these fault conditions generally dissipate a lot of power, which generates temperature. So you want a MOSFET that is really robust in these situations. Otherwise, you can end up with a burnt out MOSFET. And we've seen cases in the press in the past where you've seen people burn the shed down or the house down when charging up some of these devices. So MOSFET selection is really important.
Super, thanks Stephen. We've got another question. What specific advantages do a matched VT MOSFET provide in comparison to a larger size single MOSFET meeting the same current and voltage requirements?
I'll leave that one for Sammy. Sammy's probably best for that one.
So if you can just repeat the question to get a full understanding.
Yeah, sure. So what specific advantages do a matched VT MOSFET provide in comparison to a larger size single MOSFET meeting the same current and voltage requirements? Okay,
so the matched VT, in terms of the current requirement, the matched VT has nothing to do with the current per se. The matched VT MOSFETs are chosen so that specifically for parallel design, where two MOSFETs or more share the same current, and therefore their switching levels need to be the same, so that that sharing of the current is balanced. And therefore, these MOSFETs for a parallel design are specifically screened, chosen or selected to have a V threshold matched, so that they both, or more than two MOSFETs, if more than two MOSFETs are needed for paralleling, switch on at the same time, and therefore that current is shared equally and balanced.
Okay, thank you, Sammy. Another question, could you please present an example of symmetrical QRR curve and explain what does S less than 1 mean? So we obviously don't have an example on hand, do we? Or do you have one in the... Ah, you do there. Perfect.
Do you want me to answer that, Stephen?
Yes, please, Sammy.
Okay. So the softness factor refers to... I don't know if we can zoom in onto the top right corner picture, but there it shows the body diode characteristics in the, yes, that's correct. So the softness refers to how the diode or the body diode of the MOSFET recovers. Now, the factor of 1 refers to the time TB over TA. Now, the closer you get to 1, the better, or the soft recovery it is to the MOSFET by reducing the ringing and the spikes. And that's what we aim for. TA is pretty much dictated by the body diode itself. TB is something that we can control, where the recovery is not brushed, it is nice and soft. And those timing, the ratio between TB over TA is what the factor of 1 that we need, what we aim to achieve to give you the best recovery, or the softest recovery for the avoiding the spikes in the ringing.
Thanks, Sammy. And the next question, how do you best size and select a MOSFET in motor drive?
I can take this one as well, Stephen. So as we mentioned with regard to, first of all, the VDS rating. Now, we mentioned that normally the VDS rating of the MOSFET is chosen to fit the system voltage levels. The system voltage levels tend to be 80% of the rating. But then again, other designers may choose a different approach. Now, selecting a MOSFET appropriate for a motor control, the items that need to be looked at are the stalled current capability, as well as a startup where the high current is needed. Now, I'm not stating the obvious here, where the nominal current is normally what people look at in a MOSFET, and that nominal current tends to be 50% of the device capability. What we need to cater for, and we do, is the situations which are now part and parcel of the normal expected operation of the motor, are the locked motor, as I said, and the high current startups. Now, what we do with our MOSFETs is we provide the capability where the package is no longer the limiting factor. The olden days MOSFETs, 10 years and above, packaging was a concern and was the limiting factor for achieving high current. Nexperia MOSFETs have gone past those plastic limiting packaging devices, and therefore the MOSFET that we provide with the high current rating, the high current rating, maximum current rating, is actually verified through testing, not just by design, and therefore give you the full access to the full capability. So the situations where there's a locked current or the startup, where you need the MOSFET the most, giving you the higher current, then the LF pack does provide you with that capability. So those are the main two situations that you need to cater for: the locked currents or locked rotor and the high startup currents.
Thank you, Sammy. Next question. Why is SOA required for battery management?
You want me to answer that one, Sammy?
Either way, but yeah, go ahead.
Okay, so normally the battery management device, so it can either be two MOSFETs back to back, or it can be one MOSFET as an isolation, like a load isolator. If you imagine there's some inductance in the circuit, and for a lithium-ion cell, it can supply an infinite current for a very short period of time. This is why it's a very effective energy transfer system, lithium-ion. So you may have currents in excess of 300 amps for maybe up to 10 milliseconds. Now, as that current flows, and it may be that it's an overload current, when we try to turn the MOSFET off, there's obviously going to be some voltages generated over the inductances and resistances within the circuit, and it may not be possible to actually turn the device off as completely as you'd want. So as you switch on a MOSFET, you want for the logic level, you want the voltage to be above 1.5, 1.7 volts. And likewise, to turn it off, you want it to drop below the 1 volt. As the MOSFET gets hot, that could be as low as 0.5 volts. So you only need a 0.5 volt generated or across the system for that MOSFET not to be fully turned off, which means the MOSFET is in linear mode for that short period of time. Obviously, as you keep driving the MOSFET with a 0 volt on the gate, and that linear mode starts to limit the current, then that voltage developed across the inductances and the connections will reduce, and you turn the MOSFET off. But for a short period of time, we expect it to be in linear mode, and very high SOA rating is required.
If I add to that, if I may, there are circuits, motor control circuits, that require big capacitance in the drive itself. And the MOSFET used to enable that circuit needs to cater for the huge or the inrush current, which can be quite significant for the demanded by the capacitors, and therefore you might want to consider a soft start to that circuit, and therefore linear mode, which then results in a MOSFET required a strong SOA.
Super. Thank you, Stephen. Thanks, Sammy. Okay, so that's all the time we have in this particular session for questions. So thank you to both Stephen and Sammy for your time this morning. If you take a look below this video screen, you will see links for further information on these particular power MOSFETs, including product data sheets. You can also get in touch if you would like any more information. We do have a team full of power experts available to chat throughout the next couple of days. Just use the orange speech bubble in the bottom right of your screen, or if you prefer, you can send us an email using the blue bar on this channel. If you've got a little more time today, please do stick with us. Stephen and Sammy are with us in about 5 minutes to discuss high current MOSFETs.